Okay, let's talk briefly about the production function. You're going to see that a lot of these concepts look really similar to what we talked about for the utility maximization problem. So a production function is just a mathematical way to represent a firm's technology, how they produce the good. And it's going to give us the maximum output that can be generated for a given level of input. So here I have the quantity that the firm produces is a function of L. L is going to be labor, or the number of workers, and it could also be a function of labor and capital. Capital is going to be machinery. So it could be anything from, say, an oven in a cookie shop all the way up to a production plant. So the production function is analogous to our utility function. The utility function gave us the highest satisfaction when we consume two goods. The production function is the highest output when the firm uses different levels of inputs, like labor and capital. So here is a picture of a production function where I have output level or quantity on the y-axis, and we have labor or number of workers on the x-axis. So I'm ignoring capital for the moment. Basically, we can assume that capital is being held fixed. So if you think about a cookie shop, we're holding the number of ovens fixed, and we're seeing how does the output or the number of cookies produced vary when I change the number of workers. And here what we are seeing is that when we have 6 workers, then the cookie shop can produce 9 cookies. And this might be in thousands, so it could be 9,000 cookies, or it could be in hundreds, so it could be 900 cookies. It depends on how we're measuring that output. So one thing to take note of is the shape of this production function. It goes up more steeply and then it levels off a bit. So in other words, the slope is steeper and then it flattens out as the number of workers goes up. And this characteristic is pretty common, and we typically refer to it as diminishing marginal product. In this case, diminishing marginal product of labor. So basically it just says that when you hire an additional worker, they might produce more. They might produce a positive amount, but they produce less than the previous worker did. So the way I think about it is cooks in the kitchen. So when you keep adding cooks in the kitchen and you don't change the number of ovens, then things are going to get a little hectic. And those additional workers are not going to be as productive. And eventually it could be that you add so many new cooks in the kitchen without adding ovens that number of cookies actually goes down. Now that's not what we saw in the previous slide, but it's possible. So here's an example of a production function. I have quantity as a function of labor and capital. And I just wanted to show you that we can take this expression, which is 2 times the number of workers raised to the 1/3 power times the amount of capital raised to the 1/3 power, and we can plug in the number of workers and the amount of capital and find the quantity. So here the quantity, the maximum quantity that can be produced with 1 worker and 8 ovens, or pieces of capital, is 2 times 1 to the 1/3 times 8 to the 1/3. So that is 2 times 1, and 8 to the 1/3 is 2. So we have a quantity of 4. So an isoquant is the graphical representation of production levels given the input levels. And it's going to give us the combinations of capital and labor that produce the same amount of output. So this is exactly like an indifference curve. The concept is the same because with an indifference curve, we had different combinations of two goods that yielded the same utility level, and now we have different combinations of inputs that yield the same production level. So it's very similar. And here is an isoquant. You'll notice it looks just like an indifference curve. And we wouldn't be able to tell the difference unless we had things labeled. So typically when we draw isoquants, we put capital on the y-axis and labor on the x-axis. And so you can see that when we have 3 workers, 2 capital, we're at point C, 2 workers, 3 capital, we're at point B. 6 workers, 1 unit of capital, we're at point D. And we join those together to get an isoquant. There's also point A up here. So it looks like an indifference curve. That isoquant yields an output level of 24. And as we move up and to the right, we get to higher output levels. So the last thing I want to show you, just like I showed you with indifference curves, is that we're really in 3 dimensions here, even though we typically only draw it in 2 dimensions. So you can think of the capital labor axes as, again, laying flat on the ground. And then this third axis is going to be the quantity. So the black curves are the isoquants. This is the highest quantity. And we can fill them in like we did before to get the production function instead of the utility function. But I'm going to work backwards this time. So instead of starting from 3 dimensions, I'm going to start from our 2-dimensional graph. So here we would think of this as capital versus labor. And we have these black isoquants, but really there's an infinite number of isoquants. And so that's why we've shaded in the whole graph. So you can think of rotating this graph back to 3 dimensions, like so. And you end up with your production function. It looks exactly like a utility function. They are both curved planes. So again, this is the relationship between the production function and the isoquant. Production functions are really 3-dimensional, but isoquants are usually represented in 2 dimensions in the xy plane.